So my name is Patrick. I'm from 9-Element Cybersecurity. xHCI controller. And that means if there's no native driver, then we don't have input and can't control GRUB at all. Okay, so let's have a look. To use the input devices, you need hardware drivers, and most firmwares do have those drivers because every recent platform only uses USB devices. As everything, USB host controllers changed a bit over time. The latest one is the xHCI. And GRUB has no xHCI controller support until now. And Cobalt doesn't have any drivers, nor does it provide runtime services. So there's no input if you run GRUB as Cobalt payload. But why doesn't it affect you? So if you run on UFI, UFI has support for xHCI controllers. It's able to abstract the input and output devices using a so-called protocol. It provides boot services. That's code that can be invoked by something like GRUB or the operating system to access those hardware without even knowing about it. It also provides runtime services. And that is why the USB devices work out of the box on UFI. You just have to, so GRUB just has to talk to UFI, and then everything works. Same for the legacy BIOS. And this example, CBIOS, it also support for those kind of USB controllers. It provides runtime services. You have to call the so-called interrupt 16, which is a real mode handler. And using that, everything works out of the box, even though GRUB doesn't have xHCI support. So what we want to do, we don't want to have wrapper code. There was a nice proof of concept from Björn, who used the lib payload, put it into GRUB using some wrapper, and had almost working xHCI support. We wanted something that integrates into the existing driver model. First of all, it should work on YAML and then on Intel xHCI controllers. Our goal was to support human interface devices like a keyboard and USB mass storage devices, so that you can interact with the GRUB menu and boot from USB drives. Also nice to have feature hot plug detection. Okay, so first of all, we compared existing solutions. As already mentioned, there's CBIOS. It only has one file. It's very small code base, almost standalone. We have Core, which has one so-called Dixie. There are multiple files in it, about 8,000 lines of code, which is quite huge compared to CBIOS. but it heavily depends on UFI protocols. So we had to implement, or would have to implement, UFI protocols in GRUB if we want to use that. That's something we won't do. Yeah, there's the payload, as already said, about 2,000 lines of code. Yeah, it's almost standalone, but has a very different driver model compared to GRUB. And there's U-boot, also a well-known firmware. It also has support for xHCI and about 3,200 lines of code. We decided to use ZBIOS as reference implementation. It's written by Gerd Hoffman and Kevin O'Connor. It's LGPL version 3, so it has even a compatible license. The code is standalone, but it's written for x86 protected mode. So there's no support for paging, no support for power caching, so it will likely not run out of the box on everything else than x86. I want to show you some proof of concept, first of all, before diving into the implementation itself. You can find it on GitHub. It's open source. We have about 2,000 lines of code. We've implemented control and bulk USB transfers, which is that are the only two transfers used by GRUB. It's working on QEMU, and we've tested it on Intel Coffee Lake platform. Okay, can you see the video? Trying to maximize my screen. Let me see if that works. No. Okay, that's bad now. Yeah, it looks like I can't maximize it using this Zoom meeting. So it's pretty pointless to show it here. Yeah, what we have is that it works in QEMU, and then we're able to finally boot an ISO image, in this case, Ubuntu, over the emulated xHCI controller. Okay, so I'll skip that as it doesn't show up full screen. Yeah, let's dive into the xHCI spec. It's designed for USB 3 devices or 3.1. Supports super speed devices. And that's important note. It supports low speed devices. So there's no more rate matching hubs that are required, no more companion controller. Everything is built into this one controller. It also has virtualization support. Supports up to 255 devices. And almost everything is done using DMA. Okay, so what I'm going to skip, power management, interrupt support, and virtualization. That's all something we don't need in GRUB, but still everything works fine. Okay, let's have a look at the old controllers. So the iHCI controllers are for USB 2 devices. We have this PCI config space, which then maps a MMIO bar. And inside this bar, which is much bigger than the PCI config space, we have lots of registers, which allow it to control the controller and get feedback about its current state. And inside The DRAM, in this case it's blue, are DMA buffers, or so-called USB transfer buffers. And those buffers contain the actual data that's sent over the USB stream. And you only point to those buffers in memory using a single register in the MMIO space, and then the controller will fetch it and or fill it with data by itself. This is a quite nice feature. And now I have a look at the xHCI controllers. Yeah, it got much more complex. One reason is the increased speed. So the designers offloaded as much as possible into the memory. Again, blue boxes here are DMA memory regions. So the controller will fetch everything from DRAM or put into DRAM by itself. Most of the memory buffers you see here are set up once, and then you don't have to touch the MMIO config space never again, because this is quite slow, as there are no caches enabled on that memory range. Okay, let's have a look. What's new on this generation of controllers? I started the device context pointers. So for every device you attach, there's a slot context, and you need to point to it, and every slot context in turn points to endpoint command rings. I'm going to explain those on the next slides. Then there's one command ring that's used to execute commands on the xHCI controller, and there's one event ring. That one is filled by the controller with events that happened. It's the software's duty to set up all those pointers and allocate all those buffers before the controller can start and operate. And we will see how that works. So first of all, before we can do anything else, we need a command ring. If you're interested how this works, please check out the spec. So there's one register that's pointed to the command ring. The software then fills one of the slots or multiple and notifies the controller that something's to do by writing a so-called doorbell register inside the MMIO bar. So that means that every time you want to submit a command, you have to write a single register inside the MMIO space, which doesn't take that much time. The command buffer needs to be allocated in DMR memory. It's called TRB for transfer ring buffer. And it's a software duty to generate or mark the last slot within a special event so that the pointer can be reset to the first element. That's actually done inside the software event handler that will be notified. So every time we reach the last element, it's reset to the first. Thus, we have a ring buffer. You can see the last two, NID and EID. Those are part of the transfer ring buffer, but not used by the hardware, but they are used by the software for internal state tracking. You will find those in the code too. Yeah, and you just ring the doorbell when you have written one or multiple slots, and then the controller will fetch it from memory and execute the commands. Once it has executed something, it reports back in the event ring. So the event ring, again, is a ring buffer allocated in DMA memory. And it's written by the controller. There are two registers. The software tests if there are one or more events in this ring buffer. And if so, it processes them and updates the IRDP register, which tells the hardware that the slot is not used anymore and can be filled again by the controller using DMI transfers. So again, it's possible to process all those events by writing a single register in the MMIO bar, which is quite fast. Okay, so now we're able to submit commands and receive events from the controller, do some basic functionality. So the next important topic are slots. The device list is DMA memory, as well as the slot context. There are at maximum 265 slots. As you can see, it's the same limit as the maximum number of supported devices. And that is because for every device you attach to this controller, you need to allocate one slot. The real supported number you can read from the register, xHCI params1. And yeah, it turned out that on, for example, our Intel Coffee Lake platform, there are only 16 supported slots. And that means you can only connect 16 devices at once. And the hardware isn't possible of supporting or operating more than those at once. So the slot context is device specific and contains, for example, the number of endpoints, the device speed, and also the route through hubs. I'm going to explain that in detail later. USB transfers are always directed to one endpoint. And in order to communicate to an endpoint, we again need a transfer ring buffer. Every endpoint has its own transfer ring buffer. It needs to be allocated by software. And again, on the last command, we set a special flag so that we can update the pointer to the first element to have a true ring buffer. And to start processing, there's a doorbell register, which needs to be written as already known from the xHCI command ring. So the difference between the command ring and the endpoint command ring is that the endpoint is only for submitting transfer requests. So if you want to read or write data from an USB endpoint. Something that's important to know is that the xHCI controller does way more than previous controllers. For example, it assigns an address by itself to a connected USB device. On previous generations, you had to keep track of USB addresses yourself. So I already noted that. In the xHCI controller spec, you need to collect routing information. As you can see here, we have a root hub with multiple ports, and then we have connected multiple hubs to this camera. And we need to write the slot context and store not only the root port number, which this device is connected to, but also the chain of port numbers to the root hub. In this example, it would be 132. And this chain is called a root. This is required for the controller to know how to deal with unplug and plugging events. Okay, if you check out the repository, you will find a new file in the bus USB folder. It has an entry point called xHCI init device, about 200 lines of code. And what it does is, first of all, pass the capabilities, allocate all the DMA memory we have heard about right now, resets the controller, configures the ring buffer for commands and event handling, configures the device context, and an event segment. The event segment is required to operate the event TRBs. You will also find this struct inside the file at the end. It's the main struct holding all the function pointers for USB controllers. And you will see there's a new function called attach device. So we have added it. Only for the reason of the xHCI. And what it does is it gets called before a device is initialized. And there's another one called detach device, and it's called as part of detaching the device. Those functions are new because before all the device handling were done by the parent, but with xHCI, the controller does way more than on previous generations. So we have to invoke it too. The attach device function turns out to be essential. We have about 250 lines of code. And if you check out the code, you will see it calls the prepare endpoint function. And that does all the stuff I've talked about in the last slides. First of all, you request a new slot for the device you just plugged in. It allocates the DMA memory for the slot context and allocates memory for the endpoint command ring. And then it requests the controller to assign an address. So there's no more manual housekeeping of the USB addresses. And this function also sets up the command rings for the other endpoints, not only the first. So then again, if you look at the code, there are another essential functions, that is setup transfer, check transfer, and cancel transfer. And as you can guess, the transfer functions are used to transfer or communicate with the USB device. To be precise, it allows you to communicate with the endpoints. So the setup transfer function is implemented by GRUB xHCI setup transfer. It gets passed in the data on the destination. It starts the hardware, and it only handles bulk and control transfers, but that's enough for human interface devices and mass storage devices. We have the check transfer function, which periodically checks for the result, and the cancel transfer which might abort a pending transfer if it times out or some error happens. So this took quite a while to get it right. If you have this simple transfer consisting out 5 USB packets, like setup, and then you transfer data, and at the end you transfer 0 length packet to mark the end of the transfer. Then you need to convert it to something xHCI controller understands. This looks like that. If you want to transfer more than one data packet, it's called normal packet. Every next packet that is a normal packet, you need to set special flags, as you can see here, marked with a blue shape. The last packet needs to be marked as last. And again, then there's something special. It's called inline data. So usually you have a pointer to the DMA memory buffer that is then read or written to by the controller. But if you set this special flag, the pointer is instead used as data. So you get 8 bytes that can be filled in directly. So you don't need a DMA memory buffer if you want to transfer 8 or less bytes. All this conversion is done by the GRUB xHCI transfer function. This is another pitfall we had. So every USB device has descriptors, and that describe the device, the configuration, the interface, and the endpoints. And in USB 2, there's continuous list of endpoint descriptors, as you can see on the left side. So the code was only looking for the first endpoint descriptor and then assumed or stopped searching and assumed that all other endpoint descriptors follow. And because they have the same size, it's quite easy to iterate over them. On USB 3, there's a so-called super speed endpoint companion descriptor. And of course, it's placed after the endpoint descriptor. So this parsing and iterating doesn't work anymore. And yeah, as soon as we run our first test, it crashed in a common code, and we were quite surprised by this. So that's something we also added support for, that we skip over the companion descriptor, and then everything works fine. Okay, so what are the to-dos? We need to do some code cleanup. Some parts still assume identity mapping, where the physical and virtual address are the same. It only has been tested on x86, where the caching is no issue. We also need to fix the coding style. That's not GRUB coding style at the moment. We need to give it more tests on a wide range of platforms. And yeah, we need to upstream the code. That's something on our to-do list. And that's it from my side. Do you have any questions?
Thank you, Patrick, for that. And sorry for the audio issues.
No problem.
Meanwhile, I see that Vladimir, PH Coder, joined us. I believe I will leave the stage for Vladimir and Daniel for the question. By the way, very interesting talk. A lot of internals of USB communication and why you had to choose some paths and how to implement some things. So thanks for that contribution.
Mhm.
Thanks, Patrick, for doing this work. This is very interesting. At least I suppose Vladimir too. We are interested in getting this into GRUB. But first of all, I'm interested in did you have any issues with integration these xHCI code with existing USB code? You told about some of them, but also I would like to ask you about some issues related to the speed of USB devices 3 and 3.1. Because at least a few months ago, there was a discussion about the problems of potential integration of xHCI with currently existing USB infrastructure in the GRUB. So did you encounter this, or your solution just avoided these problems?
We only touched like 20 lines of code outside of the xHCI.c file. So it integrates very well into the existing driver model. We didn't have to change any of the other drivers or that much common code, except for the attach, detach function callbacks I already mentioned. We also didn't encounter problems with low speed devices. So usually USB keyboards are low speed or full speed devices, but they work very well with the current code.
Did you have any speed issues with USB disk or something like that?
When developing it, we had problems with timings, but that was mainly our fault because we were testing on QMO first, which sets some bits instantly. But real controllers, of course, take some time and then behave a bit different. But we couldn't find any problems.
Does it mean that QEMU requires some quirks in the code to work properly on the QEMU in comparison to real hardware?
Yeah, it because it's emulated, it instantly sets some bits or finishes transfers and stuff like that. So it's just,
do I understand you correctly that QEMU is more forgiving to some errors in the code?
Yeah, definitely. So that's another nice thing about the specification. There are lots of error codes and they're described very well. QMO usually just accepts everything, and on real hardware you usually see an error code that tells you did something very wrong, and then you look at the spec and see, spec is right, controller is right, you did it wrong.
So my understanding is that
that's actually
sorry, go ahead, Vladimir.
That's actually a very common theme with QEMU, that pretty much every controller in QEMU is very forgiving. Like graphics controller, you can skip half of the registers and it will still work, whereas on real it would just show you garbage. Same with IDE, xHCI, pretty much every controller in a QEMU is very forgiving.
Yeah, it is.
So my understanding at this point is that if you write the code which work on the real hardware, that it also works on the QEMU, and you don't need any special quirks for the QEMU itself. Okay.
Right.
Okay, perfect.
Yeah, so right now there are no quirks for specific hardware. We've tested it on QEMU and real hardware, and the same code works on both.
Okay, perfect. That's nice.
Okay, so my question is about selection of the USB stack. So you decide to choose CBIOS driver. Like, can you elaborate on that or tell a little bit more about that? Because so do you mean that it's better or to some extent easier to port than U-boot, or like I'm pretty sure Tiano core stack is complex and have so much dependencies that it's terribly unportable. But can you elaborate on that selection, and do you
Yes, of
see
course.
any kind of adoption issue of this code?
Yeah, so the code was almost standalone and very small. So that was a design decision to use it as reference. Yeah, I guess it was a good decision because it turned out to work very well. So of course we had to adapt most of the code to work with the GRUB internals. But on some parts you can still see that it's based on CBIOS.
And so how this did you make any comparison except looking at code to other stacks, to other implementations?
No, so I cannot tell if it's more secure or faster or anything.
Yeah, so from our perspective, we worked with CBIOS on PC Engine's platforms for quite time, like almost 5 years, and we saw many weird situations where some timings or some other problems, and to be honest, sometimes it is a problem of devices which are massively produced and not always comply with precisely with the specs. But sometimes our idea was that CBIOS stack is pretty much simplified, but maybe it do its work and that's good enough. Or maybe we should like start with something simple, and then if there will be really economically feasible need, then we can extend that. But as I said, like we saw some issues, and I just wonder to GRUB maintainers maybe question like how hardened is USB stack in GRUB? I'm just wondering because we had these networking issues where Daniel even said recently sent a discussion from mailing list that Michał Żygowski is famous thanks to that. And so I wonder like how hardened is the stack for USB in GRUB? Or maybe Patrick, you can also add anything because like you Daniel already asked question if you saw any performance issues or any other issues with this stack. But I just also wonder how much those stacks are validated and what's the quality of them.
I'm not familiar very well. I'm not very familiar with USB stack in GRUB, so I would like to defer to Vladimir this question, I think. Vladimir? Oops.
Vladimir, we can't hear you.
Maybe he dropped off or something like that. In the meantime, Patrick, could you say something about that? What is your opinion?
Can you hear me? Can you hear me?
Yeah, we hear you.
Yeah, we can hear you.
So unless it was hardened in recent months to a year, then no, it's not hardened. It was written without hardening in mind, and perhaps one of the problems is that if you simulate a keyboard, then you can just go into shell and do whatever you want, basically. And I'm not even. I don't think that any audit has ever been done to check that, for example, you cannot do the same thing as was done with USB on PS3, where you put some weird descriptors and do a buffer overflow.
I haven't heard about any works like that, at least at this point.
So we
Okay.
can probably do, if that helps you, we can probably do a short review of the code, but an entire audit would probably require a lot of time.
Yeah, agree. I also wonder about the performance and other stuff, and I believe the problem that Patrick pointed, that some stuff in some situation we leverage UFI services. This is this definitely makes situation where UFI services are not available the problem, because we also face that in networking stack. With UFI, it was okay. There were even problem in UFI based stack, but without UFI, it was huge problem. So I wonder how big is the interest in non-UFI based drivers, I would say, or not configuration that do not leverage UFI. I know, Vladimir, you mentioned that there are many configurations that work like that, but maybe we can think about how many problems on mailing list we have with USB.
The USB support was requested at least twice during last few months, I think, so on the GRUB devel. So I think that
you probably mean xHCI.
Yeah. I'm thinking about this one. So I think that there is some need in the community to have this driver for sure. And I think that if 9elements wrote this driver, this is very good information for the community at this point. And I would like to work with you and help you to integrate this driver into the GRUB code. Of course,
so
great.
How far it is from being merged?
I think the biggest problem right now is basically all the releasing stuff that as long as we did it, since we are in the code freeze, it basically means that we will not accept it until we are out of freeze.
But this is another question which I wanted to ask you, Patrick. What is your timeline with regards to this work?
So we have to just do some code cleanup. I guess that's pretty easy to do. Fix some compiler warnings. That's not so easy, but doable in time. And just need some good review from GRUB maintainers, how to do it, what to do, and then it's ready to go.
Okay, so I think that my expectation is that we'll be able at least cut RC1 at the turn of November and December. I hope that we'll be able to cut the release by the end of December, no later than at the beginning of January, I hope. This is our goal. I'm going to work currently on the release mostly, so I think that the work will speed up.
Ping me next week for review.
Excuse me? I didn't.
Hello?
Ping.
Okay.
Oh, ping me. Okay. Sure.
Okay, guys. So that's Patrick. Thank you very much for that talk. Thanks to 9elements for contributing that code. And we're moving to the next talk, which would be presented by Daniel. And Daniel will talk about the firmware and bootloader log exposed to higher layers.
Can you hear me now?
Yeah, Vladimir, we hear you.
Yeah, sorry, I've changed the channels. It looks like my Wi-Fi has something broken. So ping me next week for the review, and the things that you have mentioned obviously is something that like the problems that you said that it's only x86, and now in also C-BIOS probably it misses NDNS macros. it probably misses some cache and validation functions. I will probably tell where we can already put them, but without having a platform to validate it, I'm not willing to. Without having a platform to validate it, I think it's okay to merge them, even so it's not validated, because the best platform actually for validation something like this would be an old Power Mac or iMac, where you can put xHCI adapter into PCI slot.
There you can also use anything that has xHCI and core boot. So
there is no big endian platform for this.
Okay, yeah, you mean okay, NDNS macros and this kind of stuff. Okay, I just thought that you saying about basic operation of this driver.
Yeah, but I think this is already nice to have. It's not need to have, and I'm fine with the driver going in without those nice to haves. And whenever they get requested, then actually implementing them, because I think right now we don't even have full PCI driver for PowerPC.
I fully agree with you, Vladimir. That's nice to have. This is not a must.
Okay, guys. Let's try to keep a schedule and let's move on to the next presentation.
So, hello everyone. My name is Daniel Kipper. I work for Rakul and I'm a software developer and GRUB upstream maintainer. And today I would like to discuss the firmware and the bootloader log specification, which I'm working on. So the content of the presentation at the beginning, I would like to tell you why this specification, and I would also tell you some short history how the project started. Later, I will discuss the current proposal, and after that, I will move on to GRUB and Linux kernel implementation for early version of the bootloader log specification. And finally, also will tell what I'm going to do after that, and there will be also a time for questions and answers. So the idea of the bootloader log originates from the TrenchBoot project. When we were working on the TrenchBoot project, we quite quickly realized that we need some more information how the platform was configured during the boot process, because setting up the TXT in Intel TXT requires a lot of instructions, a lot of interactions in the platform, and so there is many things which should be changed, and it makes sense to transfer this information, what has changed from the bootloader to the operating system. But quite quickly realized that the bootloader itself, the GRUB, contains quite nice infrastructure to produce these kinds of logs, but unfortunately there is no way to pass this information to the Linux kernel. So we started sketching some designs, but we quite quickly realized that it seems to us that this idea can be also used by other projects. It seems quite generic. So not only the GRUB may produce such logs, but for example, firmware can produce such logs. Shim UEFI secure boot from UEFI secure boot can produce such logs, and all these logs can be passed to the operating system. So we prepared something which is much more generic and posted first version on the GRUB devel and Linux kernel mailing list at the end of May. And we prepared the next version last week and sent also to various mailing lists. We sent this to GRUB devel, Linux kernel, systemd, uboot, and coreboot mailing lists, because we think that we want to have this thing as generic as possible. So let's move on to the specification itself. This is not the specification per se at this point. This is something which we are trying to define at this point, and to try to get to a point where it should land this specification itself. So in this specification, we have two things. One is bootloader firmware and bootloader log structure header, which describes the log buffer, and we have another structure which describes the messages itself, but also its properties. So let's discuss how the firmware and bootloader log structure looks like. So as I said, this is the header, and it describes the properties of the bootloader, the firmware and bootloader log. At the beginning, we have a version, which describes the version of the bootloader log. Currently, it is version number 1. After that, we have something which is called producer. It is null terminated string. The producer means it identifies the module, the firmware, or the bootloader which produced a given log. The size of this member allows you to put ASCII UID strings. So in some cases, I think that it can be useful, especially if we think about Windows platforms, because Windows platforms or UEFI itself also use a lot of UIDs. So maybe in some cases, identification through UIDs can be useful. So that is why I decided to choose this size. After that, we have a flags a member, which can be used to store information about a log state. At least one state which can be interesting for operating system is this log was truncated or not. Because in some cases, if there is no much space in the log buffer, then a given module which produces the log may not be able to attach more messages. So in this case, it is worth notifying the bootloader reader that something bad happens and some messages were lost. At this point, maybe it is worth considering another member which will tell you which will tell you the number of lost messages from the buffer. This potentially will give you how many information you lost from the log buffer. I think this is not a must, but maybe it is worth adding. Another member is a pointer to next the firmware and bootloader log structure. Why? Because I can imagine that usually we have in the platform various modules, various boot components which may produce the boot logs. So, for example, firmware may produce own log, and after that, the bootloader may produce own log itself. So it will be nice to have an option to link one log from another. So this way, we just will pass one pointer to the top level log, which was initially, for example, produced by the firmware, and this firmware log will have a pointer to the bootloader log, which was produced by, for example, GRUB. Also, it is worth mentioning here that probably we should not change the first members of this header in the future specifications, because if we do that, if we have stable header, or at least a few members of this header, then older tools will be able to pass through whole chain of boot logs without a need to know newer versions of the specification. So that I think that it is useful property. And after that, we have something which is after this address of next buffer log, we have something which is called next underscore message underscore offset. This member has two meanings. One meaning is used usually by the firmware of the bootloader. It is used to put next message. So it points to it always points to the next message slot. And so this way, the firmware and the bootloader have an easy tool to find the end of the log and add next message. On the other hand, the operating system, for example, is able to identify the size of the total size of the log buffer using this member. So as you can see, this member has two meanings. Also, we have after that we have an array of messages, which consists of each message consists of various members. Message itself and its properties. At this point, also is worth mentioning that maybe it makes sense to add to the header the CRC or hash, or maybe even the signature. I'm not strongly convinced about the signature itself, but I think that maybe at some point makes sense to have some tools to verify the integrity of the log buffer. So I mean CRC or hash. This is not must. This is not a must, but I think maybe we should consider these members. So let's move on to the messages itself. As I said, it consists of a few members, and the first member describes the size of one message. So this describes the size of the structure, which you can see on the screen. After that, we have a timestamp, which is expressed in nanoseconds, starting from 0. From the discussion which I see is happening, I understand that it is difficult to understand what 0 means. Yes, I knew that when I was writing the email, but I wasn't sure at that point how to define this. So I'm aware that we should define what 0 means, because it will give us a chance to let's hope that it will give us a chance to correlate the timestamping from one log to another. It can be difficult because different boot components may have access or may not have access as to different timers, which have different precision, and etc., etc. So I think that this requires more discussion, and it can be difficult, but we should try to define this timestamp and reference point as precisely as possible. Next two members are stolen, let's say, from syslog, and they have a meaning similar to syslog. The first member is called level, and this member can be used to differentiate normal messages from the debugged messages, but exact interpretation of this member depends on the producer, which generated this log message. We also have something which is called facility, and this member can be used to differentiate the sources of messages. So, for example, if we have a networking module in the GRUB, we can produce. This module can produce the messages into the bootloader log, and it can use a facility to mark these messages as coming from the networking module. So this allows you to easily differentiate these messages coming from a networking module from messages which comes from different modules. So this is a very nice property. The next member is message offset, and this is the offset in the strings array, at which the message coming from the bootloader or firmware starts. It is a null terminated string. At the beginning of the strings array at offset 0, we have a string which is called type. This has a meaning similar to the facility, and will be used is used in the GRUB to store information about the modules which created the messages using a grub_dprint. So in the GRUB we will use type as a string, not the facility, but we add the facility and level to make design more flexible and more more generic, let's say. So this is more or less a message. I think that this looks like in this way at this point, but I think that it will be changing during our discussion. The next question which pops up here is less technical. The question is where to put this specification. And also various decisions has various pros and cons. So we have, I think that we have at least two choices here. We can attach this specification to existing, let's say, firmware boot component specifications. I'm thinking about UEFI, xHCI, multi-boot protocol specification. And we can make this firmware and bootloader logs structure specification as a standalone specification, which is a part, for example, Oasis standards. The problem with attaching to the existing specification is that if, for example, we choose a UEFI specification, which is first of all huge, but it is not always it is implemented on a limited set of platforms. It is getting more common and common, but it is still on limited set of platforms. So there is pretty good chance that people who works with other kinds of firmware will not be looking at this specification and may try to invent something which currently exists. So I think that this is disadvantage of having this specification in these specs. Advantage is that I think that to some extent it is quite easy to attach this spec to this specification. Maybe xHCI is the best one. I'm not sure. It requires more discussion, I think. So as I said, this requires more discussion, and I think that our decision also will influence the wording which will be used in the specification, because I think different approaches require some different wording and some different descriptions, which should be if we decide to put in existing specification, it requires to be in line with this specification. So I think that this decision which should be taken as early as possible, I think. Okay, so let's move on to the implementation which currently exists. As I said, this implementation is done for earlier version of the specification, which was planned mostly for the GRUB. But later, after the discussion, we realized that it makes more sense to make it more generic. So initially, we have a bootloader, in this case, GRUB, which collects messages into temporary buffers. Temporary buffer is allocated during the GRUB initialization, and when the GRUB works, messages are attached to the buffer. If there is no space in the buffer, then the buffer itself is reallocated using internal reallocation functions, which are quite similar to the C functions. And just before jumping to the kernel, in our case Linux kernel, we move the log buffer from the temporary buffer to the final resting place. The final resting place is allocated using something which is called relocator. It just looks for the free memory which can be used as a storage, as a final resting place storage before switching to the kernel. And after that, we copy the temporary buffer, log buffer, to the final resting place. Currently, since that moment, it is not possible to update the log buffer. I think that this is limitation of this implementation, but after some thinking, I realized that it is possible to update this buffer. Of course, we are not able to extend this buffer later, but I think this shouldn't be a problem, because just at this late boot stage, I think we will not produce so much messages. So to some extent, we are able to extend this, predict to some extent the size, the maximum size of the log buffer. The GRUB logging can be controlled through 3 variables. And the first variable is grub_log, which is used to turn on and turn off logging to the log buffer. The second variable is grub_log_debug. The meaning of this variable is very similar to the debug variable, which is well known in the GRUB, which can be used to control which debug messages are printed on the screen. And the variable grub_log_debug can be used to control which kind of messages will go into the bootloader log. And finally, we have a third variable, which is called grub_log_debug_fl. This variable allows you to enable or disable printing of files and line numbers from source code log buffer. So as you can see, you have a lot of control what is printed to the log buffer, and this gives you a lot of flexibility. So let's move on to the GRUB to the Linux kernel. We realized that at this point there is no way to pass the log buffer from the bootloader to the Linux kernel. So we had to add and extend the boot protocol, in this case x86 protocol. So we added two members to existing boot params structure, which is used to pass various arguments from the bootloader to the Linux kernel. And we added two members. One member, contains the address of bootloader log, and another member contains the size of this log. So this way, the kernel is able to identify where it can find the log in the memory and its size. We discussed also another method to pass the information about the bootloader log on UEFI platforms. And after discussion, we think that it makes sense to use configuration table to pass this information. So in this case, the firmware or the bootloader should register the bootloader log using a well-known GUID, and after that, the Linux kernel will be able to find it quite easily using configuration table functions. But in this situation, maybe it doesn't make sense to use this member in the header, which will be used to chain various logs, and we should register separate logs using separate GUIDs. It requires, I think, more discussions. The latter seems less flexible because it will be different from common case on non-UEFI platforms. So maybe we should stick to the solution which will be used on almost every platform, I suppose. And after that, the kernel may expose the bootloader through sysfs. We proposed that the file name will be produced using the producer name from the specification. Of course, this name should be sanitized to not introduce special characters in the buff. And after that, user space tools are able to parse these logs as needed. So, as I said, everything is work in progress, so there's a lot of moving parts here, and I expect that various things will be changing, but I see a lot of interest among community and industry in this project, and various people from various areas are interested in implementing this in their products. A lot of some history, you can find this quite easily. The idea was discussed initially at the end of 2019. We just discussed rough things, but first verse of specification was posted by me at the end of May. And this initiated the discussion around this functionality. Later I presented something about this thing during Linux Plumbers conference. And last week I took all comments which I got on mailing list, and also the feedback which I got during private discussions with various people, and I incorporated them and posted the message to the mailing list. So you are able to take a look at it. And you are also able to take a look to the code, which was prepared by Oracle intern Alec Brown. So you can take a look at the GRUB patches, which implement this functionality. Surprisingly, this is very small, because in general we decided to hook up to existing print functions. So I think that it works quite well. Of course, it requires some updates to accommodate currently existing implementation, but I'm happy that it doesn't require a lot of changes, and doesn't require changes in that term that you don't need to add additional calls to special functions which do logging for you. We just hook up to grab dprintf, grab print, etc., etc. So we just get all logging out of the box without major changes in the GRUB code. There is also a Linux kernel patch which updates the bootloader bootloader protocol. And also there is SLStat tool which reads the buffer log in the which is formatted in previous specification, but it also allows you to print some configuration information of Intel TXT platform. So this is what is happening around this project right now, and I hope that I will be able to actively work and continue work on this project, and there will be more people interested in and involved in development of the specification. So that's it, and I'm looking for questions.
Great, thank you very much for that. So let me start with some first thoughts. I'm like, when you're talking about where to put that, you're thinking about UEFI, ACPI, of course, like you already may have idea what I think about that. But but first concern that I see in, so let's say ACPI sounds reasonable enough, despite it is controlled by Intel. But then the question is how to support like something like Power, where there is no ACPI as far as I know.
That is why I have a big problem with this, because as I said, I would like to have this as generic as possible, and I'm not sure that it is easy to find an easy reply for this question.
I actually had similar thoughts on something similar, but for passing some other information. Have you seen the facility for adding CPA or blobs to the initramfs?
Nope. I heard about something, but I do not know details.
So what you can do is basically add a generated CPIO to initramfs, and then the tools in initramfs can pick it up not, without depending on even on specific kernel version.
Okay.
You can use it. Is it pretty much independent of the kernel?
Okay, but where to put that? The question is where to put the specification to make it, let's say, publicly available, and to make people aware that something like that exists and they can use it, and to make sure that somebody will not come and not invent the same thing but in different format.
About not inventing things in different format. Are you aware of similar things from coreboot?
I'm not sure that I understand what you mean.
There is core boot log.
No, okay, I haven't heard.
Yeah,
I haven't heard.
yeah. So this is CBMEM. I'm not sure
okay.
if Michał is here, but I don't think if CBMEM kind of provides everything here. On the other side, Coreboot gets the dedicated ACPI table. We call it boot. Michał, do you have more information about that?
Yes, there is a ICPI table called which exposes a device called boot, and it is used to reserve the memory, which is used by CBMEM. GRUB also has some support for CBMEM, but only to the extent of extracting the timestamps generated by Coreboot. So
No. I will double check, but I'm pretty sure that I have written also a tool which both writes to CBMEM log, and a tool which reads from CBMEM log inside the GRUB, not only the timestamps.
okay, then maybe my information may be outdated, but for sure there is a module that can print timestamps.
Yeah, print timestamps, and I think also add to timestamps.
Okay, that's cool.
Do you think
we'll have to check?
Okay, sorry, Michał.
Yes, please continue. I have finished talking.
Okay. Do you think that we should take a look at this CBMEM specification, and do you think that it can be useful for our use cases?
I don't think that it covers everything that you want to achieve, because it doesn't associate the particular lines with the timestamps, for example. It doesn't associate particular lines with the producer and so on. So it's definitely does not cover everything that you want to cover, but there is some room for discussion here, including like perhaps we could pull the forces together with Coreboot and actually have Coreboot adopt the same specification and then just pass everything to Linux.
Okay, so my understanding is that you suggest that maybe we take a look at this, let's call it specification, and try to extend it and make it generic.
Right. Yeah, well, first of all, as far as I know, CBMEM does not have specifications. So
I'm calling it.
okay.
That way.
Because so there is place for Daniel to propose a specification which aligns with CBMEM goals. But I see that Nico already answered to the Daniel, to your email.
Yes,
he's got his own kind of concerns and comments. I believe, like, so from my perspective, from what I see, the reception of this spec is way better than, for example, universal payload spec. So I think you are on good path. The key point is that it's very, very, very hard to align with everyone. So there have to be collateral damage. There is no workaround for that. And
that's right.
yeah, so I don't know, like, if there is, Michał, maybe you know if Google has any modification to CBMEM, or they used it by any means. But if they don't, if they use, then definitely some approval on Coreboot leadership call would be cool. If they don't use, that's maybe even easier. But then the problem is how the same concept can be adapted for UEFI platforms, which are majority of the market. Yeah. So
CBMEM is used on Chromebooks, both to expose the log to Linux and to expose the timestamps, because on some Chromebooks models there is actually a stated goal that from the time you press the power up button to the moment when you have the desktop, it's less than I think 900 milliseconds or something like this. And in order to debug where some milliseconds can be shaved off, it's the timestamps I exported to CBMM timestamp table, and the log I also completely exported to CBMM log table, and this includes both core boots log and depth charge logs. So this way, you can see if something non-standard happens.
Yeah. So Vladimir, like we are, core boot contributors, and use that many times for boot time optimization. But okay, I assume like this is native, like a native CBMM use case that Chromebooks use. I just wondered if Google has something, like custom for them, like they have their forks and Day3s of core boot, which are not upstreamed. Yeah. Same with Flash ROM. So I just wondered if they have CBMM, like a custom CBMM implementation. And then there is need for unification and specification of what CBMM does and how. And then maybe when this kind of specification will be created, then Daniel could kind of point his problem and point like trench boot problem, and maybe others have the same. And then this specification can cover also Daniel's points. That was my kind of thinking. But yeah, Daniel, so from the perspective of that you want to expose those information, and like I think it is needed also. I agree with that. But how this should be done is kind of, for me, not so clear. I would like to hear more voices from community and probably familiarize myself with the answer of core boot community. I don't know if you sent this to UFI mailing list.
Nope.
EDK to Devil. Maybe this would be good to copy them. If we want to get feedback from UFI guys.
I've seen some folks which are involved in EDK2 development, so they are on the list. And
Okay.
So I think that they are aware about my work.
Okay, I see like many people here.
Yeah.
And let's see what they will talk about that. So I believe U-boot is also important, like from ARM world perspective. But who knows, like if they have any interest in that. Anyway, great work, and like from my perspective, interesting stuff and needed stuff.
Okay, thank you.
Have you considered, instead of writing nanoseconds, writing raw timer counter, like for example just storing RDTSC value?
But the problem is that every platform has different timers, and we should know which kind of timer you used in the for the timestamping.
Yeah,
because for example, core boot uses different monotonic counters. Like you have a choice of TSC or LAPIC timer. That's each one counts with different frequencies. So
because one concern that I have is that if you start dividing by frequency for every single line that you print to this log, on an x86, dividing is already a pain, because if you want to divide quickly, you need to enable FPU, which usually you don't want to. And on some platforms, you need basically to divide manually. So perhaps it would make sense to add to the beginning of the table what is considered the main source of truth and which calibration parameters you use. Like, for example, that we use the source of truth as TSC, means value 1, and then the next field is by how much to multiply it before dividing by some power of 2.
I think that to some extent it makes sense. Yes, the timestamping problem is very difficult because especially at the boot phase, because you have so many timers. Some, as I said, some are not available. Some available for various stages. Some have different precision. So yes, I fully agree that we should think how to do that properly.
Is there any stage at which TSC is not available?
If we are talking about x86, probably no. But as I said, I would like to have this specification as generic as possible and not platform and architecture dependent if possible.
Then probably the best way is to have a field which says an anon field for which timer is considered source of truth, and then probably a second field which is calibration value, which with exact definition depending on the timer category.
Maybe yes. Yes, I'm open to this discussion. We should find the best. First of all, the most flexible solution, but on the other hand, it has to be simple as possible.
Yeah. So I think that like on x86, it should probably be TSC.
I think that potentially, yes, it makes sense.
That if some bootloader strongly prefers to use some other timer, they can still do one call to TSC and then calibrate it with what the source of truth is. We can write it down that you're not obliged to use this timer, but this is what you use as your starting point.
I think that makes sense. Okay, I will think about that, and I will take that into account during writing the next version of, let's call it, spec at this point. This is not a spec at this point.
Or it could even be something like time anon value, calibration, and then starting point. So in case of TSC, it would be the earliest TSC when this table was created.
Yeah. Okay, do we have any other questions with regards to that? Or through to the Patrick presentation?
Sounds like we exhausted topic pretty much. Do we have any other topics? I don't see any questions in chat. So I believe that's good time to ask if anyone wants to ask a question. So next week, Tuesday, we have 2 last presentations. I believe those would be, to some extent, one would be very interesting and one would be terribly boring.
Oh, no, I don't.
The terribly boring will be made by me about GRUB2 licensing.
I don't agree. I do not agree. I do not agree.
So I will present kind of greedy capitalist position about licensing of GRUB2. And like, by the way, today I read the discussion on OSFW Slack, where Trammell Hanson with Ron Minich discussed licensing for SPI SPI project. And the proposed license was GPL3 versus and AGPL, and yeah, nobody agreed to that. But anyway, like, I will leave that for the next week. And second talk will be way more interesting because we will try with Michał to show our experience from booting RISC-V, like booting platform using GRUB on RISC-V QEMU emulated hardware. And we will see what would be our experience and what kind of problems we will face. I assume this was contributed by Alexander
Yes.
Graf. he's right now in Amazon. So that's kind of interesting coincidence. If he's doing this as a part of his work, that's very interesting. That Amazon contributing to GRUB. And second thing, of course, I wonder how Amazon plans to leverage the project if GRUB is GPLv3 licensed.
Not true, if at all.
And you know, like when I'm looking at various contributors, you know, like this could be source of interesting litigations by some mad lawyers. But anyway, maybe I will not sell great ideas to the to the internet. Okay. Anyway, I believe that's it for today. Thank you very much, Patrick. Thank you, Daniel. Thank you, Vladimir. Thank you, 3M Dev team for doing this, and talk with you next week.
Thank you, guys. See you next
Bye-bye.
week. Bye.
See you next week.
Bye bye.